Hello, everyone. My name is Toghrul. I'm a contributor at Scroll, and today I'm going to be giving a short talk about the future of EVM-Equivalence. So, you probably heard about rollups, specifically classic rollups. And what I mean by classic rollups are rollups that publish a minimum sufficient data to reconstruct the state and have a trust minimized bridge with the same base layer. So some of those rollups are Ethereum compatible slash Ethereum equivalent, and I'll explain what that is in a bit. And what I mean by Ethereum compatibility or Ethereum equivalence is that they attempt to provide some or all of the features that Ethereum has, and some of those are EVM compatible or EVM equivalent. And we can go back to an article that Vitalik published a couple of years ago called Types of ZK-VM Compatibility, and we can refer to that. So there are, Vitalik described four different types of ZK-VM compatibility, and those types can be generalized. So you can not only use those types to refer to ZK zero knowledge based rollups, but also optimistic rollups. Obviously, the caveat would be that we assume that you're gonna drop the ZK part in the EVM, but the result is still the same. So the four types of the EVM compatibility that Vitalik describes are type 4, which is compatible with higher level languages targeting EVM. So think of Solidity or Viper or Phi or any other language that can be compiled into EVM. An example of type 4 EVM would be ZK Sync era. Type 3 is the next type, which is compatible with most of the EVM opcodes. So opcodes are the instructions within the virtual machine that are used to execute the state transitions. And an example of a type 3 would be linear, scroll, or polygon ZK EVM. Type 2.5, which is all of the above, plus it needs to be compatible with the EVM precompile. So if when Ethereum launched, it was lacking certain features, especially related to cryptography, and the way it was solved by adding precompiles, which are native smart contracts that can be executed cheaply on chain. So currently, Ethereum has 9 precompiles. 6 of them are pure cryptographic, and three of them are related to cryptography. And basically, a type 2 needs to support those precompiles. Type 2.5, sorry. Then there's type 2, which is compatible with the gas schedule of EVM. So every single opcode and precompile has a cost defined by the specification of Ethereum, and the gas schedule basically defines that cost. So let's say if you execute addition, a certain gas cost is subtracted from the gas that is allocated, and how much is subtracted is defined by the gas schedule. And so an EVM that is type 2 would use the gas schedule that is defined by Ethereum. And type 1, which is fully compatible with Ethereum specification. So you can think of it as just a prover for Ethereum, basically. So you can take an Ethereum block, prove it inside your prover, and it'll work. So you don't need to change anything. And yeah, I lied a bit. So I actually, if you were following, I actually mentioned 5 different types of EVM, not 4 EVM compatibility. So there are 5, but specifically why I used 4 is because 2.5 is a bit of an intermediate type. So usually, at some point, if you are type 3, you will become type 2.5. That doesn't really make much sense to just remain type 3. And but before this talk, we only care about type 2 because everything else is a bit out of the scope, and I'll explain now. So type 4 and type 2.5, so that's type 4, type 3, and type 2.5 are not EVM equivalent. So what that means is there are certain features that are core to EVM that are missing in those types. So for example, type 4 doesn't support anything other than compatibility with the higher level languages that compile into EVM. Type 3 doesn't have precompiles or the gas schedule, and type 2.5 doesn't have the gas schedule. And so it would be similar behavior to EVM, but it's not actually EVM. And then type 1 is Ethereum equivalent, which means two things. One, it's when we're talking about EVM, we don't really care whether we're compatible with other stuff that Ethereum has. And two, if we're Ethereum equivalent, we are limited to how many features we can actually introduce, because certain things are just gonna not be possible if you want to still be compatible with Ethereum. And so for type 2, currently we have two type 2s on the mainnet. It's Optimism and Arbitrum, and you can also consider all the derivatives of Optimism and Arbitrum. So, for example, Base and all the other projects that use OP Stack to deploy on the mainnet would be considered type 2 EVMs. And then you also have Scroll, Linear, and Polygon Zeek EVM, which will eventually become type 2. So they're missing certain small things. So, for example, for Scroll, we're missing a few precompiles. Polygon and Linear currently don't support precompiles, so Polygon doesn't support them at all. And Linear does support them, but they don't prove them inside their prover, which means that basically on like a purely compatibility perspective, they don't support, or like the security perspective, they don't support it. And so they will eventually, all three of them, us, Pliny, and Polygon, will become type 2s. And while being a type 2 is great, because you get all the features that that tooling for EVM, that targeting EVM has, and like all the smart contracts that are built for Ethereum can just like be ported natively, or any other EVM can be ported natively to you, and like it makes developers' lives so much easier. There are certain things that we can still improve. So one of those things is state bloat. So state bloat is famously Ethereum is famously bottlenecked by state bloat. And I'll explain what state bloat is now. And it's basically, and think of it this way, because we inherit the properties of EVM, a lot of rollups are either out of necessity or out of compatibility. Also, you inherit the storage structure that EVM uses, even though technically you can be an EVM without inheriting that storage structure or similar storage structure. You can use a completely different storage structure, but all of us still do use that structure. And basically, we sort of inherit the same bottleneck. And in some cases, it's even worse because we use a different storage structure for various different reasons. And so the state bloat can be actually separated into two different problems and two different bottlenecks. So the first bottleneck is state size growth. It's purely the size of the data that you need to store for accounts, for both smart contracts and end user accounts. And it's a problem for hardware constraints protocols. So, for example, Ethereum needs to be run on very, very low powered machines. And therefore, it's a problem for them because if the state grows too large, it won't be able to fit into, like, let's say, 1 terabyte or 2 terabyte SSD. And so you would end up with a protocol that is too big to be run on, like, what I would like to call commodity hardware. But for rollups, that's not such a big deal because the assumption is that not everybody using a rollup needs to run a full node, and therefore that's not a problem for us. And the second problem that is related to state bloat is I/O latency, and that is a problem that affects L2s as much as it affects L1. So what I/O latency is the time the execution environment spends waiting for the data to be fetched from the storage. So, for example, if a smart contract tries to read the balance of a certain account within an ERC20, let's say, during the execution, it has to wait for that data to be fetched before it can proceed with the execution. And so the problem is that the larger the state grows, the longer it has to wait for that data to be fetched. And therefore, there's a certain bound on how much the state can grow, or like how big your actual tree can be before it becomes too slow. And therefore, you can only execute a certain amount of transactions per second. And one of the solutions to the problem is parallelization. And again, parallelization can when people talk about parallelization, they mostly refer to execution parallelization. But there's a second type of parallelization, which is IO parallelization, which is a similar but also a bit different. So when you're talking about pure IO, pure execution parallelization, you're just talking about like pipelining transaction execution, and basically just executing them simultaneously. But if your storage is actually not optimized for parallelization, then you still have the same bottleneck. And so what's IO parallelization does, it optimizes the storage to ensure that you can access things in parallel. And what that means is that state reads and writes can be parallelized within those pipelines, and basically your execution it doesn't result in your entire execution instance halting, but only specific pipeline. And so you can essentially think of it this way: if you're executing 4 transactions in parallel, and one of them needs to read something from the storage while others don't need to, or like need to read something else, then only that one will hold, and so you can still continue executing on the other pipelines. And you can even take it further and combine it with mandatory access lists. So Ethereum currently has access lists, which was introduced by EIP 2930, if I'm not mistaken, which basically an access list just describes all the slots within the memory that within the storage that you're trying to access. And if we make that mandatory, we can actually prefetch those slots. So what that means is that basically we at the beginning of the execution you can execute and you can just start another instance which just pulls the relevant data for those transactions from storage, which means that by the time you get to the point where you need that data, it's already in memory, so you don't need to pull it from storage. Another thing that you can improve upon is to introduce local fee markets. So local fee markets is something that Solana has introduced recently. And so I'll describe what local fee markets after like I describe the problem. So the problem is that currently EVM transactions compete with for gas space in a unified global fee market. So think of it this way. So let's say if there's a hot new NFT drop that everyone wants to claim for like the next 10 blocks, but you as a user are trying to use Uniswap or some other or Curve or any other do anything else on Ethereum, you're essentially competing with those users for block space, which means that you're paying extra amount to be included in the block space, even though you're not competing for that congested block space, which is not a very efficient pricing, not the most efficient auction model when it comes to like global processing transactions. And so what local fee markets do is basically they enable a more granular auction to be held, which basically means that if you have different completely unrelated interactions with 2 different accounts, they don't affect the gas fee prices of one another, so they compete in 2 different auctions, which means that people can still compete to claim that hot new NFT drop without actually affecting the price that a user pays for a simple transfer or like a Uniswap transaction or any other operation on chain that doesn't involve that NFT drop. And that can actually improve the user experience drastically. And I think it's something that is worth exploring. Another thing that we need to look into, and like EVMs would have to adopt at some point, is multi calls. So what multi calls are is the problem that most of you probably encounter is if you're using an ERC20 token, you have this horrible UX problem of having to approve in a separate transaction to the one that you then used to interact with another smart contract, which means that you need to send 2 transactions and pay twice the amount of what you would have if it was 1 transaction. So what multi-calls allow you to do is they enable to a single transaction to make multiple unrelated smart contract calls. So if you have a multi-call, now you don't have to do those separate approve and transfer from transactions. You can pack them into one transactions and just do that in one transaction, and that improves the UX drastically. And I think uh, it will also enable certain use cases that are currently not possible because of the way that Ethereum transactions are structured. And finally, another thing that you can also do, I call it EVM plus, but you can use different names about to refer to it, is just adding new features. So why should we stop at the features that EVM currently has? Why can't we just add new features? So, for example, like think of it this way: your protocol's execution environment can be a superset of the EVM feature set. So what that means is you can support all the EVM features, so still be EVM equivalent while adding new features on top of it to make certain use cases possible or improve certain UX properties, etc. So think of like the capabilities here are virtually unlimited. So, for example, want to add a new cool opcode that will improve a certain application or a certain use case, go for it. Like, why not? As long as you support everything else that EVM does, nothing prevents you from doing that. Or want a new cryptographic precompile? Yeah, great. Do it. Why not? And it's actually already happening. So it's an EIP 7217, which adds a new elliptic curve that was actually proposed by a local team called Clave, was accepted, and some of the rollups have already adopted it, and some of the rollups will adopt it, and which means that now most of the EVM equivalent or compatible rollups are going to have supersets of precompiles versus what Ethereum has. And that's what I'm talking about. And you can expand it further and do other interesting, cool things that Ethereum can't support or doesn't want to support for various different reasons, including additional complexity, etc., etc. And so, in conclusion, I would like to say that being EVM equivalent doesn't mean that your execution environment has to be ossified and you have to follow whatever Ethereum does. There's still a lot of room for experimentation where you can either improve things or add new features that Ethereum lacks, and therefore build an environment that is substantially better, both in terms of performance and UX. Thank you for listening. And yeah.